Welcome back to Normal Procedures for the AgustaWestland AW109SP, an English learning podcast for aviation professionals. I'm glad you're here for episode 2. In our last episode, we walked through the philosophy that sits at the heart of every safe flight, and then we went step by step through the pre-flight inspection, making sure the aircraft was airworthy before we ever touched the cockpit switches. Today, we pick up right where that left off. You're standing next to a cold helicopter. The walk-around is done. The aircraft checks out. Now it's time to go inside, power everything up, and bring those two Pratt & Whitney Canada PW207C turbine engines to life. This episode covers the engine pre-start checks, the normal engine start procedure, the quick engine start option, what to do if a start goes wrong, and then the systems checks that confirm every system aboard is ready to carry you safely into the air. These are the moments that separate a professional crew from an inexperienced one. The engine start sequence on the AW109SP is not complicated, but it rewards understanding. And that understanding is exactly what we're here to build. Before you command an engine to start, you need a cockpit that's alive and a crew that knows what it's looking at. The engine pre-start phase is about exactly that, systematically energizing the aircraft and verifying that every display, every warning system, and every control is functioning correctly. Think of the pre-start sequence as the aircraft introducing itself to you. Each step is the helicopter saying, "This system is working, this display is accurate, this warning channel is open." Your job is to listen carefully and confirm what you hear. The first thing you do when you enter the cockpit is bring the avionics master online. The MSTR AVNX switch, Master Avionics, is your gatekeeper for the entire avionics suite. Setting it to ground, or GN, gives power to the avionics systems in a controlled, safe configuration without enabling all the full flight modes. This protects sensitive equipment during the power-up phase. Once avionics power is established, you turn your attention to the battery. The BAT switch goes on. This is your baseline power source. Without it, nothing else works. But here's something important. If you have external power connected to the aircraft, a ground power unit or GPU, the battery is automatically disconnected when external power is plugged in. That's a design feature, not a bug. The helicopter protects the battery from unnecessary discharge. When this happens, you'll see a BAT off caution message on the display. That's exactly what you want to see. It's the system confirming, "I see external power, and I've protected the battery accordingly." If your battery needs charging, not an unusual situation if the aircraft has been sitting for a while, you'd set the BAT switch to EPU, which allows the external power to charge the battery while it also powers the aircraft. Now you energize the generator buses, Gen Bus 1 and Gen Bus 2, and the generators themselves, Gen 1 and Gen 2. The generator buses distribute electrical power to the various aircraft systems. Think of them as the main highways of the electrical system. The generators, once the engines are running, will be your primary power sources. Right now, they're being set to their ready positions so they can come online automatically when the engines start. The inverters, ANV1 and INV2, convert DC power from the electrical system into AC power for certain avionics and instruments that require it. Both go on during power-up. Once the avionics are up, your two engine display units, the EDUs, will illuminate. These are the primary cockpit instrument panels for engine data. EDU 1 shows the cruise page with your critical power parameters. EDU 2 shows the main page with oil pressures, temperatures, fuel pressure, hydraulic pressure, and fuel quantity. But right now, you're not just reading them, you're testing them. The AW109SP has a built-in test function that runs both EDUs through a complete self-check. You initiate the test from either unit, and what follows is a very important sequence. The master warning light and master caution light will illuminate. The voice warning system will announce engine fire. The engine fire warning lights will illuminate on the panel. All of this is the system proving that its warning pathways are intact. If the test completes without errors, you'll see confirmation messages: EDU 1-bit pass, EDU 2-bit pass, DAUA bit pass, DAUB bit pass. That acronym, BIT, stands for built-in test. And that pass confirmation is your assurance that the data acquisition units, the display units, and the monitoring channels are all healthy. The aural warning generator, the AWG, is one of the most important safety systems on a helicopter. It's the voice you'll hear if something goes wrong in flight. During pre-start, you test it by selecting and holding the AWG switch to test. What follows is a complete recitation of every aural warning the system is capable of generating, in a specific sequence. Rotor low. Engine 1 out. Engine 2 out. Fire engine 1 fire. Fire engine 2 fire. Warning. Rotor high. Autopilot. Engine idle. Over torque. Airspeed. Landing gear. Decision height. 200 feet. Altitude. You're not just listening to make sure sounds come out. You're confirming that every channel is active, every tone plays at the right pitch, and the sequence is correct. A silent or incomplete AWG test is a no-go item. If you can't hear those warnings in the cockpit, you can't safely fly. The AW109SP uses an electronic engine power lever system. The physical levers in the cockpit connect to motors that move the fuel control unit, and the engine trim toggles on the pilot's collective allow fine adjustments. During pre-start, you verify that these trim toggles move the levers correctly in both directions, and then you confirm the levers are positioned in the flight position, ready for the start sequence. If the remote control system has any fault, you'll see a PLA motor caution message. The power levers can be operated manually if needed, but the remote control is your primary interface, and it needs to be working before you start. You also confirm that neither engine is showing a PLA caution, which would indicate the power lever isn't where the system expects it to be. With both number 1 PLA and number 2 PLA caution messages suppressed, you're clear to continue. The remaining pre-start checks cover a range of systems, each one important, each one with a clear purpose. The fire extinguisher bottle switch sits centered, armed, but not discharged. The push button covers over the engine fire extinguisher buttons are checked for their condition, guarded, in place, intact. The static source switch stays in norm, guarded. This switch controls whether your pedostatic system reads outside air pressure from the normal ports or an alternate source. In normal operations, it stays on norm. It's only moved to the alternate position if the normal ports become blocked. If the aircraft has an emergency locator transmitter, the ELT switch should be confirmed in the arm position. This means the ELT will activate automatically in the event of a crash, but won't transmit during normal operations. The intercom system, or ICS, gets tested. You switch to backup mode, BK up, then to EMER, check that you can hear and communicate, and then reset to norm. This confirms that if your primary ICS fails in flight, the backup pathway works. The main hydraulic servo switch is confirmed in norm. The cabin ventilation is set as required for crew comfort. Landing gear indications show 3 green lights, nose, right, and left gear all confirmed down and locked. The red gear unsafe light is out. You run the lamp test, selecting and holding the lamp switch, which illuminates all the indicator lights on the APMS panel and the red gear light simultaneously. This confirms that every bulb is functional. It's the equivalent of pressing the test button on a smoke detector at home. You want to know the lights work before you need them. The OEI training switch is confirmed off. The altimeter is set to local pressure. Fuel quantity is checked, you already confirmed fuel during the walk-around, but you verify the cockpit indication matches what you know. The load share switch is set as operationally required. The NR rotor speed switch is set to 100% for start. This is the reference position for the start sequence. And finally, the rotor brake is tested, engaged to confirm the rotor BRK caution message appears, then disengaged to confirm it clears. The rotor brake must be fully released before you start the engines. With all of that complete, the cockpit is alive, tested, and ready. Now we start the engines. Starting a turbine engine is one of the most precisely engineered sequences in aviation. Understanding what's happening inside the engine as you work through the start procedure transforms it from a list of switch positions into a story you can follow in real time. The AW109SP has two Pratt & Whitney Canada PW207C turboshaft engines, each rated at approximately 900 shaft horsepower. They use a full authority digital engine control system, the FADEC, which the AW109SP calls the ECU, or Engine Control Unit. The ECU manages the fuel flow, the starting sequence, and the protection systems entirely automatically in normal operation. Your job during a start is to set the conditions, monitor the parameters, and intervene if something goes wrong. Either engine can be started first. The AW109SP has no requirement for a specific sequence. By convention, Engine 1 is typically started first, because that's how the checklist is written. But operationally, if there's a reason to start Engine 2 first, position on the ramp, wind direction relative to exhaust, or crew preference, that's perfectly acceptable. Before you touch the engine mode switch, you need to prepare the fuel system for that engine. The fuel valve for Engine 1, Fuel Valve 1, goes open. When the valve handle is vertical, it's open. Horizontal means closed. This is not accidental. The vertical position looks like a pipe allowing flow. Horizontal looks like a barrier. Once you can visualize that, you'll never confuse them again. With the valve open, you turn on fuel pump 1. The electric boost pump pressurizes the fuel line from the tank to the engine, ensuring there's positive fuel pressure at the fuel control inlet. You'll see the fuel pump 1 caution message disappear. That caution was telling you the pump was off. Its absence now tells you the pump is running. And you check the fuel pressure gauge on EDU2 to confirm positive pressure. Now you move the English 1 mode switch from OFF to idle. This is the trigger. This is the moment the engine comes to life. What happens next happens fast, and you'll be watching several parameters simultaneously on EDU1's start page. N1, the gas generator speed, will begin climbing. You'll see a start legend appear vertically on the display, confirming the starter motor is engaged. The starter is essentially a small electric motor that cranks the engine core up to a speed at which it can sustain combustion. Very shortly after N1 starts climbing, the ignition fires and fuel is introduced. You'll see TOT, turbine outlet temperature, begin to rise. The IGN legend appears on the display, confirming ignition is active. This is light up, the moment combustion begins. One of the things you're watching closely during the start is when the rotors begin to turn. Before N1 reaches 40%, the rotor should already be rotating. This tells you that the engine is driving the gearbox correctly and the main rotor system is coupling normally. If the rotor has not begun to turn by the time N1 reaches 40%, that's an abort criterion. Something is wrong with the drivetrain or the gearbox. Once N1 passes 40%, you check engine oil pressure. It should be rising. The PW207C engines can generate very high oil pressure during cold starts, up to 200 pounds per square inch, and that's within limits for up to 10 minutes. As the oil warms and its viscosity decreases, pressure will come down into the normal operating green band. The related caution here is about oil temperature. Until engine oil temperature reaches at least 10 degrees Celsius, you must not allow N1 to rise above 90%. Cold oil doesn't flow and distribute heat the same way warm oil does. Applying power before the oil is warm enough is a reliable way to reduce engine life. Similarly, transmission oil pressure will rise as the main gearbox begins working. The caution for the transmission is similar. If oil pressure is above 70 pounds per square inch, you remain at idle until it decreases to below that threshold as the oil warms. Cold, thick gearbox oil generates high pressure. Let it warm. Let it thin. Then advance the power. At exactly 50% N1, the engine is self-sustaining. Combustion is generating enough energy to accelerate the engine without help from the starter motor. The ECU knows this, and it automatically cuts the starter. You'll see the start legend disappear. The IGN legend disappears as well. Ignition is no longer needed because the engine is burning continuously on its own. You'll also notice the DC generator 1 caution message disappear. This is because the engine-driven generator is now producing power and has come online. The starter drew heavily from the electrical system during cranking. With the engine running and the generator online, that load is gone. As the main rotor begins to turn, the main hydraulic system pressure rises. You'll see this on EDU2. The hydraulic servos that power your flight controls require this pressure. Without it, you're flying without hydraulic assistance, which on a helicopter this size means very high control forces. If the hydraulic accumulators were discharged, which can happen if the aircraft has been sitting for a while with the hydraulic servos activated, you'll briefly see main util CHRG and EMER util CHRG caution messages. These tell you the utility hydraulic system is recharging its accumulators. Both messages will disappear on their own once the systems are charged. No action required, just observe and confirm. There's an important caution that applies throughout the start sequence until rotor speed reaches 85%. Avoid any cyclic movement except to prevent the blades from hitting their stops. At low rotor RPM, the blades are partially unloaded and can flex significantly. An aggressive cyclic input at low RPM can cause blade strike, a blade contacting the fuselage or rotor head stop. This is not a theoretical risk. It's a documented cause of accidents on rotor aircraft. Below 85% NAR, the cyclic stays center unless an emergency demands otherwise. After the starter cuts out and the engine accelerates on its own, N2, the power turbine speed, will stabilize at the idle speed of approximately 65%, plus or minus 1%. At this point, you confirm all engine and transmission parameters are within limits, and you move the English 1 mode switch from idle to flight. With the mode switch in flight, the ECU commands the engine to accelerate to the flight idle speed, and N2, which is coupled to the main rotor through the gearbox, climbs to 100% NR. 100% rotor speed is your normal, steady operating point on the ground between starts. Now you repeat the entire sequence for engine 2. Fuel valve open, fuel pump on, mode switch to idle, watch N1 rise, confirm light up, watch rotor acceleration, monitor oil pressures, wait for auto starter cutout at 50% N1, confirm hydraulic pressure, wait for N2 at idle, advance to flight, confirm N2 and NR at 100%. When engine 2 advances to flight, there's a specific engagement moment to watch. As N2 increases toward 100%, engine 2 must engage with the main rotor drive. A properly functioning engagement is smooth, you'll see N2 climb and stabilize, and the torque reading will come up normally. If the engine appears to be at positive N2 but shows near zero torque, that's a non-engagement. The engine is turning but not driving the gearbox. That requires shutting down the non-engaged engine first, then the engaged engine, and a maintenance inspection before the next flight. With both engines running and N2/NR stabilized at 100%, you do a few final housekeeping items. If you were using a GPU, you disconnect it and close the external power door. The EXT-PWR on and bat off caution messages will clear when external power is removed and the battery automatically reconnects. You confirm the bat switch is on. The battery should now be online and being maintained by the engine-driven generators. The master avionics switch moves from ground to norm. This fully enables the avionics suite for flight operations. And the co-pilot's displays are checked and verified. Both PFDs and MFDs are on, showing correct data, with no failure indications. 2 engines running. Both generators online. Avionics fully powered. You've successfully started the AW109SP. The normal engine start takes each engine through idle before advancing to flight. This is the preferred procedure in most circumstances because it gives you a gentle warm-up opportunity and the chance to observe each parameter sequentially. But there are situations where you want to compress that timeline. A quick engine start goes directly to flight, bypassing the idle hold, and it can start both engines in immediate succession rather than one at a time. When is a quick start appropriate? 2 conditions must both be met. First, the outside air temperature must be warmer than 0 degrees Celsius. Cold-soak engines benefit from the gentler warming of an idle start. Second, you can use the quick start for a warm engine, one that has been running recently and hasn't fully cooled down. Hot section components are already at temperature, which means the expansion and contraction stresses of a cold start aren't present. The quick start is also appropriate when the operational situation demands rapid departure. It's not a shortcut you take because you're running late. It's a defined procedure for defined conditions. The sequence is similar to the normal start, but you open both fuel valves and turn on both fuel pumps before initiating any engine start. Then Engine 1's mode switch goes directly to flight instead of idle. Engine 2 follows. Its mode switch goes to flight as soon as Engine 1's DC generator load drops to 200 amps or less. That threshold exists because the starter motor draws heavy current, and starting Engine 2 while Engine 1's starter is still pulling maximum amps would overload the electrical system. The monitoring requirements are identical to the normal start. You're watching the same parameters, looking for the same abort triggers, confirming the same milestones. The difference is just the speed of progression through those milestones. No matter how well-designed the FADEC-based start sequence is, there are situations where a start must be stopped before the engine reaches self-sustaining speed. Knowing these abort criteria cold, without having to think about them, is one of the marks of a professional turbine pilot. The 5 conditions that require an immediate abort are: light up. The appearance of ignition and TOT rise does not occur within 15 seconds of initiating the start. If you moved the mode switch and 15 seconds have passed with no ignition, there's no point continuing to crank the engine. You hear abnormal noises during cranking. A turbine engine starting correctly is relatively quiet until light up, and then has a characteristic acceleration sound. Grinding, scraping, banging, or any unusual mechanical noise is an abort trigger. TOT rises beyond start limits. The start limit is 650 degrees Celsius maximum continuous, with a transient limit of 875 degrees for 2 seconds. If you see TOT approaching or exceeding these values, you're looking at a hot start, too much fuel burning before the engine core is spinning fast enough to cool it. Hot starts damage the turbine section. The rotors have not begun to rotate by the time N1 reaches 40%. As we discussed, rotor rotation at low N1 confirms the drivetrain is coupling correctly. No rotation by 40% is an abort. N1 or N2 exceeds their limits. An overspeed during start is an automatic abort. And finally, the engine hangs. A hung start is when N1 stagnates below 54% and stops climbing. The engine isn't accelerating towards self-sustaining speed. This can indicate insufficient starter energy, a fuel control issue, or a hot section restriction. Whatever the cause, if N1 stops climbing before 54%, you abort. The abort is clean and deliberate. The ENG mode switch goes to off. That commands the ECU to begin shutdown. If the engine does not begin to respond to the shutdown command, a rare but possible scenario if the ECU has failed, you go to manual backup. The engine power lever goes to off, the fuel pump goes off, and the fuel valve closes. You have physically cut off fuel at both the pump and the valve. After an abort, the engine cannot simply be restarted immediately. Fuel may be pooled in the hot section, residual fuel that didn't fully combust. If you attempted another start on top of that pooled fuel, you could get a significantly worse hot start than the one you just aborted. So before any restart attempt, you follow 2 steps, a 30-second fuel drain period where you simply wait, and then a 30-second dry motoring run. The dry motoring run is exactly what it sounds like. You motor the engine, turning it with the starter motor, without fuel or ignition. The purpose is to clear any trapped fuel or vapor from inside the engine before attempting another start. Think of it as blowing out a match before relighting it. The residual fuel inside the engine, if left in place, creates a fire or explosion hazard on the next start attempt. The dry motoring run physically pushes that fuel through and out of the engine with airflow. The setup is methodical. Engine governor goes to auto. Mode switch to OFF. Power lever to OFF. Fuel pump off. Fuel valve closed. And here's a step that's easy to overlook. The ignition circuit breaker on the overhead panel is pulled out. This is critical. You're about to run the starter with the fuel valve closed. The last thing you want is for the ignition system to accidentally fire and ignite any residual fuel vapors in an uncontrolled way. Pulling the igniter circuit breaker ensures ignition cannot occur during the dry run. With all that set, you press and hold the starter push button on the engine power lever grip. N1 climbs. TOT, which was previously elevated from the aborted start, will begin to decrease as fresh, unburned air flows through the hot section, cooling it and purging the residual fuel. After the required motoring period, you release the starter button and reset the ignition circuit breaker. Now the engine is clean, cooled, and ready for another start attempt, subject to the starter duty cycle limits in the limitations section. With both engines running and all parameters in limits, you move to systems checks. These are not redundant verifications of things you already know are working. They're active function tests that exercise each major system and confirm that it will respond correctly when you actually need it in flight. There's an important mindset here. When you do a systems check, you're not just watching gauges. You're deliberately inducing conditions, switching things off, redirecting flows, changing configurations, and then confirming that the system responds exactly as designed. You're stress testing the aircraft while you're safely on the ground. The AW109SP's hydraulic system for flight controls has 2 independent channels, Servo System 1 and Servo System 2. Each provides hydraulic power to the flight control servos. Normally, both operate simultaneously. If one fails in flight, the other provides full backup. To verify this, you start with the servo switch in norm, both systems operating, and you make small, deliberate movements with the cyclic, collective, and pedals. You're checking that the hydraulic pressure drops during these inputs are equal for both systems and don't exceed 70 pounds per square inch. Equal drops tell you both systems are sharing the load symmetrically. Then you switch to SOV2 off, which shuts down Servo System 2 and leaves only System 1 operating. You repeat the same control movements. Pressure drop should still be within limits, and critically, you should feel no increase in control forces, no discontinuity in movement, and no coupling between different controls. What you're confirming is that System 1 alone can do everything both systems do together, because in a real hydraulic failure, that's exactly what it will need to do. You repeat the test with SOV1 off to verify System 2 independently. And then you check the pedals in the single system configuration. The tail rotor servos are specifically checked to confirm they're unboosted when only one system is operating, as designed. Finally, you return the servo switch to norm with both systems online. The AW109SP's fuel system has two independent tanks feeding two independent engines, with a crossfeed system that allows either engine to draw from either tank. This redundancy is essential. A failed fuel pump in one tank doesn't mean that engine starves, because the crossfeed valve can supply it from the opposite tank. Testing this system is a systematic exercise in confirming that the crossfeed logic works correctly. You set the crossfeed valve to auto, then turn fuel pump 1 off. The crossfeed valve should automatically open, confirmed by the XFEED advisory message, and the engine-driven pump on engine 1 should maintain adequate fuel pressure on its own. You'll confirm this by watching the N1 fuel pressure gauge. No caution for engine 1 fuel pressure should appear, because the engine-driven pump is sustaining it. You restore fuel pump 1, the crossfeed closes automatically, and you repeat the test for fuel pump 2. The logic is symmetric. There's also a more demanding test. Both electric fuel pumps off simultaneously, with the crossfeed valve manually closed. In this configuration, the engine-driven pumps, mechanical pumps driven directly by the engine accessory gearboxes, must sustain fuel delivery to both engines on their own. You confirm engine parameters remain stable throughout. This tells you that even if every electric fuel pump failed in flight, the engine-driven pumps would keep the engines running. The crossfeed valve is then exercised through open and auto positions to confirm the advisory messages appear and clear correctly. The AW109SP's electrical system is primarily DC, direct current, but certain avionics and instruments require AC, alternating current. Two inverters, INV1 and INV2, convert DC to AC on demand. You test each inverter by switching it off individually and confirming the appropriate caution message appears, and that the remaining inverter is maintaining 115 volts AC on both AC buses, readable on the EDU2AUX page. Then you restore each inverter and confirm the caution clears. What you're checking is both that the inverters generate power, and that the system can sustain AC power with either one failed. The Remote Control Panel, RCP, manages how the avionics systems are routed to your displays. It has three key subsystems you test: the AHRS, Attitude and Heading Reference System, the ADU, Air Data Unit, and the GPS navigation source. Each one has three positions: a selection of System 1, a selection of System 2, and norm, which means both systems operate normally with automatic crossfill. The test for each is the same: rotate to position 1, confirm the appropriate same warning appears on both PFDs indicating that both sides are now displaying data from the same source, rotate to position 2, confirm the opposite warning, and return to norm, confirming the warning's clear. Why does this matter? Because in flight, if one AHRS, one ADU, or one GPS fails, you'll select the working system and both displays will show data from it. The test confirms the switching logic is functional. An RCP that can't switch sources is a dangerous single point of failure. The Automatic Flight Control System, AFCS, is one of the most sophisticated systems on the AW109SP. It's a 4-axis autopilot with full authority in pitch, roll, yaw, and collective. Before every flight, it must pass its own self-test, called the pre-flight test or PFT. You confirm the APMS panel shows all push-button lights extinguished, except for the AP1 and AP2 lights which show their off captions, and the PFD indicates who is the pilot flying. Then you press the test push button and step back from the controls. This is important, during the AFCS PFT, do not touch the flight controls. The test sequence moves the controls slightly in a specific pattern to verify servo authority and feedback. If you're holding the controls, you'll interfere with the test. After the test runs, you should see a message on the IDS, the Integrated Display System, confirming AP1 PFT completed and AP2 PFT completed. If a test failure or degraded autopilot message appears, you run the test once more. 2 consecutive failures means the autopilot is grounded until maintenance clears it. With the PFT passed, you engage both autopilot channels AP1 and AP2 by pressing their push buttons on the APMS panel. The OFF captions extinguish. The autopilot is armed and ready. The miscellaneous section wraps up the system's check sequence with a collection of individual verifications that don't fit neatly into the larger system categories, but are equally important. Pitot heat is tested individually for each probe. You switch it on, confirm the generator load meter shows a current spike, proof that power is flowing to the heater element, confirm the pitot heat advisory message appears, and confirm the pitot fail caution does not appear. Then you switch it off and confirm the advisory clears. A pitot heater that doesn't draw current isn't heating. And an unheated pitot tube in clouds or rain will give you unreliable airspeed, one of the most insidious instrument failures possible. Communication and navigation frequencies are set on the RTU and audio panels for the departure. The ADI's attitude direction indicators are cross-checked between pilot, co-pilot, and the standby ESAS. All 3 should agree. A disagreement between attitude indicators requires investigation before flight. The compass system goes through a similar cross-check. Pilot's heading reference, co-pilot's reference, and the ESAS standby compass must all agree within acceptable tolerances. The MAG/DG switch should be confirmed in the MAG position, magnetic heading mode, so the AHRS is correcting against the magnetic field rather than operating in a pure gyro mode that drifts over time. Altimeters are verified for automatic baro setting at local QNH, and cross-checked between pilot, co-pilot, and ESS. All 3 should read within a few feet of each other. Vertical speed indicators confirm 0. The radio altimeter should read the actual height off the ground, somewhere between 0 and 5 feet if you're on a level pad. Finally, the NR switch, rotor speed selector, is tested in all 3 positions. From auto at 102%, you select the 102% fixed position and confirm rotor speed remains stable, then return to auto. This confirms that the rotor speed governing system responds to pilot commands correctly. And any additional systems the operation requires, helicopter terrain awareness warning system, traffic advisory system, FES synchronization, are configured as needed for the flight. Let's pause for a moment and consolidate what we've covered in this episode. The engine pre-start sequence is about energizing the aircraft safely and systematically, and then proving that every monitoring and warning system is functional before you expose the aircraft to the stresses of an engine start. The normal engine start is a monitored event, not just a switch sequence. You're reading the engine's story as it progresses, watching N1 climb, confirming light up, monitoring oil pressure, respecting the temperature limits that protect the engine's life. The abort criteria exist because turbine engines are precision machines that communicate their condition through specific parameters. When those parameters fall outside the expected range, the engine is telling you something is wrong. Listening to that message and aborting, rather than pushing through, is what protects a valuable and safety-critical piece of equipment. The dry motoring run is a simple but essential clearing procedure. Never skip it after an aborted start. The consequences of restarting into pooled fuel are severe. And the systems checks are not formalities. They are the final verification layer before you commit to flight. Each one tests a real failure mode, and confirms that the redundancy built into the AW109SP actually works. In our next episode, we'll move forward in the normal procedures sequence to cover before takeoff checks, ground taxiing, and the takeoff itself, both the hover takeoff and the rolling takeoff. We'll examine what changes in the aircraft configuration as you prepare to leave the ground, and what the pilot is managing in those critical first seconds of flight. Until then, keep studying. Keep questioning. And remember, in aviation, understanding the why behind every procedure is what keeps you safe when the procedure itself isn't enough. This has been Normal Procedures for the AW109SP. I'll see you in episode 3.